Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on calculus of variations, lecture number 4, in which I will solve the isoperimetric problem. Now, we solve a problem. Problem is define isoperimetric problem in calculus of variations. Find the closed plane curve of given length which encloses maximum area. Now we solve this. Firstly, we define isoperimetric problem in calculus of variations. Let us suppose we have to find the extremum value of this integral. Integration limit a to b capital F x y prime dx. This is number 1. We have to find the extremum value of this quantity. Means this integral. Subject to condition that integration limit a to b is small f x y prime dx equal to constant. This is number 2, where capital F and small f are functionally related. Then instead of finding the extremum value of 1, means extremum value of this integral, we find the extremum value of integration limit a to b. Firstly, we write this function plus lambda into this function and dx, where lambda is a parameter. This makes the problem more easier to solve. This concept is called isoperimetric problem in calculus of variations. In the nutshell, we have to find the extreme value of this integral and another integral equal to constant, and this integral and this integral are functionally related. Then instead of finding the extremum value of this integral, we have to find the integral of linear combination of this function and this function, and it will make the problem easier to solve. Then this concept is called isoperimetric problem in calculus of variations. Now we solve the second part of the problem. Second part, let us consider AB be a given curve such that coordinates of endpoints A and B be x0, y0 and x1, y1 respectively. Firstly, we find the area enclosed by this curve x equal to x0, this vertical line, this x-axis, and vertical line x equal to x1. So we have to find area of this portion. Let the RS be dx and height of this strip be y. Then area of this strip will be y multiply dx. That is, the area of the elementary strip will be y multiply dx. Therefore, area enclosed by the arc AB, x equal to x0 vertical line, x axis and vertical line x equal to x1 will be sum of all elementary areas means integration limit x equal to x naught to x1 y dx. This is number 1. We will discuss the case for which the integral 1 is extremum. Since we know that ds square equal to dx square plus dy square implies that ds by dx whole square, dividing both sides by dx square. This is 1 plus dy by dx whole square implies that ds by dx equal to 1 plus this derivative is denoted by y prime and here square root implies that ds equal to square root 1 plus y prime square dx, integrating both sides from x naught to x1 limit, x naught to x1 limit, and this is ds with the elementary arc. Sum of all elementary arc will be the length of the arc AB, that is S, equal to integration x naught to x1 limit 1 plus y prime square dx. This is number 2. Given that length of AB equal to constant, let this is L. Therefore, S equal to integration limit x naught to x1 square root 1 plus y prime square dx equal to L. This is number 3. Now, we use the technique by using the process of solving isoperimetric problem, that is to find the extremum value of, here we have y dx, here square root 1 plus y prime square dx. So we take first this y plus lambda parameter square root 1 plus y prime square dx integration x naught to x1. Let this is I. This is number 4. Since integrand part contains y and y prime, therefore 4 may be written as integration limit x naught to x1 y plus lambda square root 1 plus y prime square dx equal to integration limit x naught to x1 function of y prime dx, and this is equal to I. This is number 5, where f y prime equal to y plus lambda square root 1 plus y prime square. This is number 6. Since f does not contain x, therefore for extremum value we use the Euler's condition as follow. F equal to c plus y prime partial derivative of f with respect to y prime implies that f minus y prime partial derivative of f with respect to y prime equal to c implies that f equal to this quantity y plus lambda plus y prime square minus here y prime partial derivative of f with respect to y prime. Here y is treated as constant because we are differentiating with respect to y prime partially. So remains lambda 1 by 2 square root 1 plus y prime square multiply 2 y prime equal to c. Here 2 cancel, so remains y plus lambda square root 1 plus y prime square minus lambda y prime square by square root 1 plus y prime square. This equal to c implies that y multiply 1 plus y prime square plus lambda 1 plus y prime square minus lambda y prime square by 1 plus y prime square. This is the LCM. This equal to c and implies that y square root 1 plus y prime square here plus lambda y prime square minus lambda y prime square by square root 1 plus y prime square equal to c. Here this quantity and this quantity cancel, implies that y multiply square root 1 plus y prime square plus lambda equal to c square root 1 plus y prime square implies that y, we take this left side minus c common square root 1 plus y prime square equal to minus lambda implies that y minus c equal to minus lambda by 1 plus y prime square root. Let this is number 7. Let y prime equal to 10t. This is number 8. Therefore, putting this value in 7, we get y minus c equal to minus lambda by 1 plus 10 square t square root. This is equal to minus lambda by sec square t square root. This is equal to minus lambda by sec t equal to minus lambda cos t. Let this is number 9 from 8. Here y prime equal to dy by dx equal to 10t implies that dy equal to 10t dx. Let this is number 10 from 9. We get dy minus c equal to d minus lambda cos t implies that dy is constant 0 minus lambda d cos t implies that dy equal to minus lambda, this is minus sin t dt, implies that dy equal to lambda sin t. This is number 11 from 10 and 11. We get left side equal, therefore right side will be equal. 10t dx equal to lambda sin t dt. Here this is sin t by cos t dx equal to lambda sin t dt, implies that dx sin t cancel, here cos t dt, here lambda, integrating we get here integration of dx is x. Let we use constant d minus d here, lambda integration of cos t is sin t. This is number 12. Squaring 9 and 12 and then adding we get here x minus d whole square plus y minus c whole square. This is lambda square sin square t, here lambda square cos square t. So if we take common lambda square sin square t plus cos square t, that will be 1, only remain lambda square in right side. Here in 12 x minus d whole square, in 9 y minus c whole square equal to, in 12 right side lambda square sin square t, in 9 minus square means plus lambda square cos square t, implies that x minus d whole square plus y minus c whole square equal to lambda square sin square t plus cos square t implies that x minus d whole square plus y minus c whole square equal to lambda square. This is number 13. Equation 13 is an equation of a circle whose center B, D, C coordinates and radius equal to lambda. The constants in 13 may be obtained from initial conditions. Also, from 13 it is clear that for extremum value of the area of the closed curve, we must have the closed curve to be a circle. So our problem is solved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.